This video is going to discuss the concept of ionic bonding. From what you remember in terms of our lecture on ions, remember that every atom would like to have a full valence shell. And so here's an image where we have sodium. If you notice, sodium is starting with just one electron, and chlorine is starting with 7. So let me freeze that. And because at this point, sodium with its one electron in its valence shell has not fulfilled the octet rule, and chlorine with 7 valence electrons in its outer shell hasn't fulfilled that sort of noble gas configuration, they can work together to actually make that happen. And as you see in this image, that one valence electron that sodium has is then lost and given to the chlorine. And this allows now the sodium to have 2 shells instead of 3, but that second shell has all 8 valence electrons, and it has reached nirvana. For the chlorine that started off with 7 valence electrons, remember valence electrons are electrons on the outer shell, it wants to have 8, it gets that 8th one from sodium, and now it has reached noble gas configuration. And just as a reminder, as these electrons are lost and gained, remember now the atom is becoming an ion, and that ions that have a charge. So sodium still has the same number of protons that it started off with, but it now has one less negative electron. And for that reason, you'll notice that sodium becomes a positive charge. There's that positive, that means that it has one more proton than it does electrons. Chlorine, on the other hand, has just gained an electron. That means that it has one more negative charge than it started off with, because remember, those electrons are negative, and therefore it now has a negative charge. In this situation, both ions have reached that noble gas configuration. They now have a positive and a negative charge. And as you know, positive and negatives are attracted to each other. And as a result, you now have the sodium attracted to the chlorine because of that positive and negative charge. And then with that said, we can show that as a dot diagram. It might be a little bit easier than always drawing all the different shells and all the different electrons, to just focus on the valence electrons, because remember, it's the valence electrons that are actually doing the moving. And just as a reminder, remember that sodium had that one electron in its valence shell at the very beginning. Chlorine had 7. And so sodium simply loses it and gives it to chlorine, and we can see that in this dot diagram. So when this happens, we call that an ionic bond. Ions can bond together, and when they do, there is a symbol that represents that, and that symbol is called a chemical formula. And so in this case here, whenever we write a chemical formula, we always want to write the cation first. That's usually the metal. Remember, that's the plus charge. And then the anion. And the numbers are written as subscript to represent the number of ions that are bonded together. And so in my scenario over here, you see that I have a sodium, so I'll write the chemical symbol Na, and I have a chlorine. I'll write it as NaCl. I write them together, making sure I write the capital letters for each of the elements, but you notice I'm not putting a number here, and the reason I'm not putting a number here is because whenever there's 1, we assume that it's just 1. We do not indicate a number. So now let's take a look at a second example. Oh, I'm sorry. let's talk about how it is that we actually name them. So in this case, we always write the name of the cation first and then the anion. And when we write the anion, we always end it with "ide." So in this case, this is called sodium because Na is sodium. Sodium chloride. There's that ending of IDE. Remember, the Cl is originally chlorine, but because it's now an anion, we call it chloride, sodium chloride. And just so you know, this is what we know as table salt. We eat quite a bit of sodium chloride. So what does that look like in terms of a particle model? So we can draw atoms as circles. And in this case, you'll see that you have a yellow sodium with a plus charge being attracted to a blue chlorine, and we more or less draw two circles close to each other. Below here in this diagram, you see a lot of sodium chlorides, and they're more or less attracted to each other because remember, all these positive sodiums are attracted to these negative chlorines. Okay? So now let's try a different one. In this case, we have magnesium and we have chlorine. If you take a look at your periodic table for magnesium, you'll notice and draw the Bohr diagram, you'll notice that it has 2 valence electrons. And you ask yourself, has this magnesium reached nirvana? Has it reached that noble gas configuration? And the answer is no, because remember, it wants to have a full valence shell. And in order to get a full valence shell, it needs to have 8. There's one exception, and that exception is the first shell, which only requires 2. So in this case, the magnesium has 2 valence electrons. It has not reached that noble gas configuration. And so you ask yourself, is it going to be easier for that magnesium to lose 2 electrons or to gain 6? And most of you are probably going to be saying that it's easier to lose 2. So let's just keep that in the back of our head for a moment. Here I have chlorine. Chlorine, if you notice, it has 3 shells. And in terms of its valence electrons, it has 1, 2, 3, 4, 5, 6, 7 valence electrons. Again, has it reached that noble gas configuration? Has it fulfilled what we also call the octet rule? And the answer is no, because remember, it wants to have 8 valence electrons in its shell, and it only has 7. So if it could only get 1 more, it would have reached that noble gas configuration. So having said that, we can already start predicting what could possibly happen. Now, in terms of any sort of chemicals, there is no such thing as just one atom of anything. And so in my next slide here, you might notice that I have a whole version. Let me use that arrow. I have a whole stockpile of magnesiums. And that means that I can manipulate these in order to have as many as I want. I have multiple layers of them. So using this screen here, I'll go ahead and reduce it so that it's perhaps easier to see. Perhaps I won't either. Is that we can then manipulate what we have. So let's start by having, in this case, 1 magnesium. There's my stockpile, and 1 chlorine. All right, so with that said, let's take a look at what we could possibly do. If this electron right here can transfer over to this chlorine, does the chlorine now have 8 valence electrons? It has 1, 2, 3, 4, 5, 6, 7, and 8. So that means this chlorine has reached nirvana. It has reached that full valence shell. So that's good. But, and just keep in mind, this chlorine now has a negative charge because it gained 1 electron. But now this magnesium still has 1 valence electron. Is it reached nirvana or that noble gas configuration? And the answer is no, it hasn't. And so what we can do is we can add another chlorine. So let me go ahead and get rid of these. Let's see if that works, okay? Remember, you have multiples of every atom. And so in this case, I have this electron leaving the magnesium and going to a second chlorine. And so in that case, we have now this chlorine having 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And then just as a reminder, remember that these electrons are no longer there, that this shell is now completely disappeared, and we now have a magnesium that has a full valence shell, being that second shell. Now, all 3 of these ions have reached, are now ions, and they have reached that noble gas configuration. Because magnesium lost 2 electrons and chlorine gained 1, we make sure to show those charges. Here's what that would look like as a dot diagram. Remember, I was showing you that you have 2 valence electrons for magnesium and chlorine has 7. And so each one of those electrons from magnesium is transferred to a different chlorine. You can have as many chlorines and magnesiums at your disposal. You simply need to make certain that those valence electrons eventually come to being a full valence shell. So here is what our diagram would look like that we had just said, where we have 1 magnesium, we have 1 chlorine, 2 chlorines, and they have transferred their electrons. The magnesium has transferred its electrons to the chlorine. So now how would I write that as a chemical formula? So remember, I always write the cation first. The cation is the positive ion, and so that would be magnesium. And now take a look. I have 2 chlorines, and so I signify that I have 2 of them by writing a small subscript on the bottom right-hand corner. So it's written as MgCl2. Let's try the next one. Oh, and just one more thing. How would that look? That would look like this if you have just particle models where you'd have 1 magnesium and then 2 chlorines. Let's work through our last example. Our last example is one where we have aluminum and oxygen. Again, we ask ourselves, has aluminum reached that noble gas configuration, or does it fulfill that octet rule? And when we look at our valence electrons, because it's all about valence electrons, I see I have 1 valence electron here, 2 here, and 3 here. That means that aluminum does not have the 8 valence electrons that it is looking for to have a full valence shell. So you ask yourself, is it easier to lose 3 electrons and have them the shell beneath that be the full valence shell, or is it easier to gain 5? And remember, you're always saying that the smallest number is the easiest option. In terms of oxygen, we have 6 valence electrons in oxygen. Again, you ask yourself, has it reached that octet rule? Is it reached nirvana? And the answer is no, because remember, it wants to have 8 valence electrons, and it is missing 2. So here's a situation where we most likely are going to know that it just needs to, that the oxygen needs to have 2 electrons and the aluminum wants to get rid of 3. So this is not a perfect match, but remember you have as many electrons, as many atoms at your disposal that you want to use. And so in this case, let's try what we can do with 1 aluminum and 1 oxygen. And let's see how that works out with our actual electrons. So we can have this electron be transferred over to this oxygen. And we can have this electron be transferred over to this oxygen. And this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. It has reached nirvana. It has that full valence shell. This oxygen is content. Because it gained 2 electrons, it's now more negative, because remember those electrons are negative. It has a -2 charge. So this oxygen is content, but is this aluminum content? And the answer is no. The reason is that this aluminum still has that 1 valence electron that it wants to get rid of. So in that case, we have the ability to give it another oxygen. So let's go ahead and scooch in another oxygen. Remember, you have as many oxygens at your disposal as you would like. And in this case, I'll go ahead and line it up right over here to make it a little bit easier. In this case here, we can now have this aluminum lose that electron and give it to that oxygen. There we are. Okay, so the aluminum has managed to lose all 3 of its valence electrons. This shell, remember, is no longer here because all the valence electrons left. 3 electrons left. That means that this aluminum has a +3 charge, and it has reached nirvana. It has reached that noble gas state. However, oxygen has not. It at this point only has 1, 2, 3, 4, 5, 6, 7 electrons. This means that it needs to have 1 more electron. Where is it going to get that electron? It needs to get that electron from something that's going to give electrons. And we know that aluminum is happy to give electrons. So at this point, we just happen, as I told you, you have as many aluminums at your disposal as you want. So let me get rid of these other aluminums and just put them in the corner since we don't need them. And in this case here, and I'm going to get rid of this as well. That way we have a little bit more space. There we are. So we have this aluminum that can now give electrons to the oxygen, and it does. There we are. So it has given this 1 electron to oxygen. Now this oxygen has the 8th electron that it's looking for. So that means that this aluminum has reached its full valence shell. The oxygen and the 2 oxygens have, but in this case the aluminum still needs to lose those 2 electrons to gain to have a full valence shell. So in that case, what is going to be happening is that we're going to see if 1 more oxygen does the trick. And I'll move these oxygens away. There we go. So in this case now, we have aluminum that wants to get rid of 2 electrons and oxygen that happens to want to get 2 electrons. This is where our story comes to an end. There we are. So it has lost this electron to the oxygen, and it has lost this electron to the oxygen. Let's check whether or not our numbers are right. 1 electron, 2, 3, 4, 5, 6, 7, and 8. Aluminum has managed to lose all 3 of its valence electrons, so that shell disappears and it now has that inner shell that's the full valence electron. So what's happening now is we now have an example of what we call an ionic compound. And in this ionic compound, we're going to do a count of what we're going to see. So in this case, we have aluminum being our cation. How many aluminums did we need? We needed to have 2. I write that as a subscript. Then we have oxygen that is gaining those electrons. How many oxygens do we see? We see 1, 2, 3. Remember, they're attracted to each other because of these positive and negative charges. So that is the chemical formula for aluminum with oxygen. How would we actually call this? So the name that we would give that is we would call it aluminum oxide. Remember, it ends with an IDE. And if you were to draw a particle model of that, it would look like this.